Hi guys, welcome to our first Physics 163 activity for the semester. I wanted to introduce you to computational activity to begin with because we're in the world of COVID, and so it made sense to make the first activity not necessarily a face-to-face activity. The good news is this activity doesn't require a lot of knowledge from the material that we're studying this semester, which is the business of electrical interactions, magnetic interactions, and light. So all it requires is that you know how to calculate the field produced by a charge and the force that that field creates. So let's have a look at it. So the idea is we've got this pair of charges. One is an electron and one is called a positron. A positron, if you haven't heard of them before, is the antiparticle of the electron. So it has the same mass as the electron, but it has a charge that's exactly the opposite. So that means the electron charge is minus 1.6 times 10 to the negative 19 coulombs. The charge on a positron is precisely plus 1.6. Well, 1.602 ... times 10 to the negative 19. It's the same exact charge as the elementary charge on an electron, but with a plus sign instead of with a minus sign. So the idea is these guys orbit one another. They go around in a circle like that, and so we're going to calculate that motion. So the idea is to work with this library. So there's a link in the assignment. Okay. So let me go full screen here so you can see. So in the left-hand screen, you see the GlowScript program. You guys, no doubt, use GlowScript in Physics 153 to study the motion of particles and objects under various forces. We'll be using it even more in Physics 163. And it's quite simple. If you didn't end up using it very much in Physics 153, let me know, and I'll point out some tutorials and introductory material you can use to get used to the coding. But basically, you can create these geometrical objects like spheres. In this case, we're going to be dealing with two spheres. You can see them here in this right-hand view. There's a red sphere and a blue sphere. The red sphere is the positron. It's created by this line. And the blue sphere is the electron. It's created by this line. You can see here I'm assigning the charge on the positron and the electron. And I'm calculating some numbers. There are questions sprinkled through the text, like why is there only one mass? Why does it have this value? So if you think about these questions and you include those in your write-up, I don't expect a very long write-up, but just answers to some questions, some explanations. We'll see here in a moment that the rubric tells you exactly what you need to provide. You start out with a momentum that each particle has. And the idea is to get the thing going in a circle. So when the program's running, when the complete program is finished, these guys will orbit one another in a circular path. And you can get the time it takes to go around using the graph here below, because this is going to graph the x-coordinate of the positron. The x-coordinate of the positron as a function of time. Right now, it looks like it's just 0 because the thing's not moving, and so the graph can't autoscale. But once it starts moving, the graph will autoscale nicely, and you'll see a nice graph of x versus time, and then you can get the time it takes to go around from that graph. Now, you'll notice here that I've got this thing called blank. I define a vector called blank, and then in the program, I define the electric field on particle 1 by particle 2 is equal to blank, and then the electric field on particle 2 from particle 1 is equal to blank. What I want you to do is to get rid of the blank and replace that with actual code that calculates that electric field. So you use the code in the book as an example, or use the formulas in the book to figure out how to calculate that electric field. Then once you've got the fields, you can calculate the forces. Once you've got the forces, you can use the momentum update formula from Physics 153, which I'm sure you'll all remember, to calculate the change in the momentum, and then therefore get the new momentum. And once you've got the new momentum, you can calculate the update to the position of the particle using the position update formula. And then this graphs the position of the positron as a function of time, and then you can see that graph here. So that's the idea. You're just going to, we have starter code here. Almost everything's already done, except you got to fill in the blanks. So the idea is to fill in those blanks and get the thing to calculate correctly. If you have any questions, you're obviously welcome to ask those anytime. In class, we're going to spend time going through a similar problem, and just to warm up your programming juices a little bit and get you comfortable with the environment if you haven't used it very much. The rubric here shows you the pieces. So the first is computational correctness. Does the program actually work? The second is evaluating the results. Have you checked? How did you validate that the program worked? In this case, the idea is to look at that graph and see if you can use the values in the graph to validate that the thing's behaving as you would expect it to behave. Now, the theoretical learning outcomes for the course, there's like 12 of them, I think, or something. I forget the exact number, but the first two have to do with the relationship between field, force, potential, and energy. That's the bubble diagram. And in this program, the relationship that shows up on the bubble diagram that's relevant is the connection between field and force. So theoretical learning outcome 1 is, do you know how to explain how do you compute the force given that you know the field? Theoretical learning outcome 2 is, can you calculate fields produced by various distributions of charges? So that's this one. And obviously, in this case, you've only got 2 charges. So the field at charge 1 is the field produced by charge 2. The field at charge 2 is just the field produced by charge 1. So you are just calculating the field at one charge due to the charge of the other charge, right, at its location. And then computational learning outcome 1 is, can you calculate fields? It's tied exactly to TLO2, except it's, can you do this using a programming language like Python? Can you calculate these fields programmatically? And then CLO3 is, can you calculate, given that you've calculated the fields, can you calculate the forces and then compute motion? So CLO3 is about computing the motion of charges under the influence of the fields produced by all the other charges. Anyway, that's the idea. So those are the grading points on the rubric that you'll be evaluated on. And we'll talk a little bit about how the grading system works. In my section, we're going to be using something called Critic. But you could use this rubric without Critic. Critic is just one way to do the grading part. So that's really all I have for you. So we'll see.